This is the week 2 workbook. Let's recap some of the basic. Stay Ohm's law. First, write down the equation. V equal to IR. And then you should state voltage equals current multiplied by resistance. And usually this is how the simple circuit and how Ohm's law is verified. V. What does each symbol represent? V represent the voltage. Now, you can also say it is the potential difference. And the unit, of course, is volt. I represent current. And the unit is ampere. R, it is resistance. And the unit is ohm. From here, you can say, what is the physical meaning of resistance? And it's if you look at V equal to IR, if V is a constant or it is fixed, so the current and resistance. So the resistance is actually measure how strong the material opposite the flow of electric current. What I mean is, if a material have strong or large resistance, it means it opposite the current, so the current will be small, and vice versa. So to put it down here, you can say resistance measures how strongly a material opposite the flow of electric current. What I mean, if you look at R equal to V for I, from R equal to V over I, 1 ohm means 1 volt per 1 ampere. Assume this is a resistor, and if we know there's a potential difference V across the resistor, and we know the current passing through the resistor is I, so we can say the resistance R is equal to V over I. But the question is, what determines the resistance? It means if a circuit requires certain resistance, how can we make this specific resistor? Now let's look into the physics and the material science. Except superconductivity, all materials has resistance. Even though we use copper or aluminum to make the wire, but there's still very little resistance. So now imagine you have a wire. It has some resistance. And now we start measure the resistance, and we find this is R. Now, if we double the length of the wire, what we will find? And we'll find the resistance double, provided they have the same cross-section area. So if we consider this one, what happens to resistance if the length increases? We can say the resistance increases. Next, we compare another scenario. This time, the cross-sectional area increases. So just like your water pipe, the area get bigger. So this one increases. And this time, you have the same length. And in this case, what we'll find is the resistance reduce. So we'll say the resistance in this case decreases. So Ohm's law say that V equal to IR. It means once the resistance is determined, the V and the I, they are proportional to each other. So the question is, what determines R? And R is proportional to the length of the materials and the cross-section of the material. The proportional constant is called resistivity, and this one is material dependent. So resistivity describes how strongly a material resists current. And the symbol is rho. Incidentally, this is the Greek letter RHO, rho. What is the unit? We have to go back to the definition. From here, we can say rho equal to RA over L. So the unit of rho is the unit of R multiplied unit of A and multiplied unit of L. And this is ohm meter square meter. So this is ohm meter. So the unit of resistivity is ohm meter. And write down the relationship between resistance and resistivity. So this is the one. Let's look at the energy source of a circuit again. Now imagine you have a battery here, and this provides a voltage. So you have a voltage V across the load, and this is your battery. Now the current I provided from the battery should accord to the Ohm's law, V equal to RL. Now we can ask a question. If the load reduces and if the V is a constant or fixed, So what happens is it will force the current increase. Now the issue is, can the battery keep supplying the required current if the load resistance reduced? And the answer is no, not necessary. And very often there's a limitation of the current which a power source can supply. So in the circuit design, we have to first assume two ideal sources. First is ideal voltage source, and we usually put this one as a circle, and then we put the positive, negative here. And this source we will put EMF. EMF is another way to say the potential difference provided from the voltage source. It will maintain a fixed voltage and allow the current to vary depend on the load. So this is the ideal voltage source. In a laboratory, the typical power supply can act as an ideal voltage source up to a certain level. So that's why you will see in the laboratory power supply, there's a two setting. One is your output voltage. I mean, this is the voltage you want to fix. The other is the maximum current. I mean, this is the maximum current it will provide. As long as the outside resistance is not so low, this can be maintained. For example, the set voltage is V and the set maximum current is I. So what I mean is R equal to V over I. This R here is the lowest resistance, such that this power can supply a constant voltage. Next, let's look at another type of source we call the ideal current source. Ideal current source cannot be visualized as a simple like a battery or power supply. It is a complicated circuit. Now, it can maintain a fixed current, and the voltage will adjust depend on the load. So what happens is, first, this is the symbol. There's an arrow here. Let's go back to our example of power source. So this is the laboratory power supply. For example, we set our voltage as 10 volt and we set our maximum current as 1 ampere. This is a variable resistance. Now, let's calculate the minimum load. RL 10 ohm. So what happens is, if the R is larger than 10 ohm, the I output can be calculated as 10 volt over RL. So it means because it's bigger than 10 ohm, so the I will be less than 1 ampere. So in this case, this output will behave like an ideal voltage source. I mean, as long as the R is bigger than 10 ohm, you can have any resistance outside, and the current will just keep alternating or adjust according to the Ohm's law. Next, if the load is less than 10 ohm, now put it as an example, 5 ohm. So I, if you use Ohm's law and if you fix 10 ohm over 5 ohm, 10 volt over 5 ohm, you will get 2 ampere. But remember, this already larger than the maximum current you set, which is 1 amp. So this is impossible. So in this case, what happens is the power supply can only provide 1 ampere. So this will become 1 ampere, and you have 5 ohm. So what happens is now the output voltage will reduce to 5 volt. So it means now it is the voltage adjust depends on the load, and this is no longer a ideal voltage source, and it become a ideal current source. So as long as the outside load less than 10 ohm, it become an ideal current source. The current maintain constant, but now this time the output voltage will adjust itself. Here we are going to look at the most important rule in circuit analysis. It's called the Kirchhoff current rule and the Kirchhoff voltage rule. First, look at what is Kirchhoff current rule say. Here is an example of a very simple but real circuit. And in this circuit, we can first identify some junction, say this point and this point. In circuit analysis, we call this node, N-O-D-E. So in this circuit, we can identify there's 1, and this is another node, 2. Next, we want to find we call the loop. This is called a loop. This also called loop. And you can always see, if you consider the outside here, this is another loop. And we give this a special name. We call this super loop. First, let's look at Kirchhoff current rule. Kirchhoff current rule says, if this is a node here, the current flow in. So in this example, 1, 2, 4, 5, 1, 2, 4, 5 is equal to the sum of the current flowing out. So in this case, it is 6 and 3. And this rule based on one basic physics, which is the conservation of electric charge, because current is way of change of charge. So if we just consider in 1 second how much charge flowing into this junction, it must equal to the number of charge flowing out to the junction, because the charge must be conserved. In the Kirchhoff voltage rule, we look at the loop. So here we have a loop. This loop starts from A, B, C, D, and A back. Now, we can choose our loop either clockwise or anti-clockwise. It doesn't matter. And we're saying is when we analyze those voltage along this loop, we will see the sum of all voltage rise is equal to the sum of all voltage drop. So this is a state of conservation of energy. Because if you think about voltage is the energy per unit charge. So therefore it is a different way to say conservation of energy. Let's look at this example. we first simplify this circuit as 12 volt, and this one, the equivalent resistance is 1 plus 2 plus 3 is 6 ohm. So the current here is 2 ampere. It means this is 2 amp, this is 2 amp, and this is also 2 amp. The potential difference here is V equal to IR. I is 2 amp, so this is 2 volt. Here 2 times 2, 4 volt. Here 2 times 3, 6 volt. Now the Kirchhoff will say, when we analyze this one, we can see what is the voltage rise and what's the voltage drop. Let's first analyze the total voltage drop. The total voltage drop along this path, it is 2 volt, 4 volt, and 6 volt. When the analyzing path passing through the battery, the voltage increases. So the voltage rise is 12 volt. So that is what the Kirchhoff voltage law say. Now, when we apply the Kirchhoff voltage law in a more complicated circuit, there's a very slightly different rule, which we'll go into it a little bit later. Let's recall an ideal voltage source will always supply the same voltage, V, and the current will adjust according to the Ohm's law. So I will be adjusted by the Ohm's law. So it doesn't matter your load resistance. If it drop, it means if this reduce, the current will increases. For the ideal current source, it will supply a constant current, I. It doesn't matter what outside resistance it is. So the voltage this time across the low resistance will adjust according to the resistance. And we also know the power supply we use in the laboratory behave close to the ideal voltage source, as long as the current is not bigger than the maximum current we set, or the maximum current the power supply can provide. And also the power supply used in the laboratory can behave like an ideal current source, as long as the load resistance is not too big. Now let's ask this question: what is the real battery should behave? And we know the real battery, it won't behave like an ideal voltage source. So we'll model the real battery as if the ideal EMF source. So this is the EMF in series with a so-called internal resistance. And this is how we will model our battery. And this internal resistance is inside your battery. So this is what you will measure the 2 points. If you just measure the voltage at these 2 points, and we call this voltage, we call it terminal voltage. Now, when you connect a load to the battery, this is what happens. RL. So now you can see this will behave like a potential divider. Why? Because this is your EMF, and if we withdraw our internal resistor here and our load, this is RL, this is R. So if we measure this point, this voltage is exactly the voltage we measure back to here. So this is so-called terminal voltage, and in our case, they are equal. And you can see what you measure, the terminal voltage will be less than the EMF, because it will like measuring a voltage at a potential divider. So let's put the number in our question. So EMF is 12 volt, internal resistance is 1 ohm, the load is 5 ohm. So we can first reduce our circuit into one resistance, it means the equivalent circuit, and this will be 6 ohm. This is 12 volt, so we know the current passing through this circuit will be 2 amp. So if we have 2 amp current passing through here, this time we can say the voltage across the load, it is V across the load, it is the terminal voltage, and it is equal to 2 amp times 5 ohm, so it's a 10 volts. Now we can get this 10 volts by just apply the usual formula for potential divider. So the V is proportional to EMF 12. The proportional constant is 1 plus 5, because you try to measure the voltage across the 5 ohm load. So the numerator is 5, so you will get 10 volts. So exactly the same answer. Where is energy loss inside the battery? So the energy loss is known as internal resistance, and it will turn into thermal energy. Why is the internal resistance important when modeling real electrical systems? It is because if you look at the real battery here, the internal resistance is a reflection of very complicated electrochemistry happening inside the battery. So the R here is a number to model this complicated reaction. And what we find is that when the battery gets older, okay, we'll find the internal resistance will increases. So the consequence is the terminal voltage will drops, and this is consistent with what our everyday experience, because when the battery is getting older, when we measure the terminal voltage, we'll find the value drop. Here are some practices. We have a copper wire, and you want to find the resistance. So resistance is proportional to the length, inversely proportional to the area, and the proportional constant is called resistivity. And now you substitute 1.7 times minus 8, and this one is 2 meters, and this one, remember, this one is 1 times 10 to the minus 6 meter square. Incidentally, the unit of resistivity is ohm meter. So you will get, this is 0.034 ohm. Internal resistance, you have a 9 volt EMF, so this is 9 volt, the EMF. Internal resistance is 1 ohm. This is for your battery, and this connected to a load, and the load is 8 ohm, and you want to find the total current. So first reduce this circuit into the simple, which is 9 volt 9 ohm. So the current is 9 volt 9 ohm and 1 ampere. The terminal voltage, there are two different methods. Method 1, we use Vt equal to IRL, the load resistance. So this is 1 amp, 8 ohm, so this is 8 volt. Method 2, now we can apply the potential divider formula. So the Vt proportional to 9, and the proportional constant denominator is 1 plus 8, numerator is 8, so it's 8 volts. To calculate the power delivered to the load, we can just say the V here is 8 volt, so P equals to VI, so it's 8 volt, and this 1 ampere, so this is 8 watt. Of course, you can also use I square R and substitute 1 square, and this is 8 ohm, and you will also get 8 watt.